Hello everyone, this is Sai Dheeraj and we have Roshan Pranav along with us. We are from SRM Institute of Science and Technology, Vadapalani campus and from second year CSCB. We are here to talk about pipeline hazards. Let's start with the introduction of pipeline hazards. We'll understand about pipeline hazards in computational architecture. We'll start with knowing the definition of pipeline. So it is a process of arrangement of hardware elements in such a way that simultaneous execution of more than one instruction takes place in a pipeline processor so as to increase the overall performance. So obviously what happens here is when an operation in an instruction stream it doesn't wait for the operation in the previous instruction stream. So in such cases the performance is obviously increased because there is overlapping of instructions taking place. We'll now talk about definition of pipeline hazards. So those situations are called hazards that prevent the next instruction in the instruction stream from executing during its designated clock cycle. So hazards will lead to the decrease in the performance of the system. Let's understand why. Why? Because like each instruction in the instruction stream has to perform its operation or execution only within a particular designated clock cycle. So when it doesn't perform in the designated clock cycle, pipeline stall takes place, and because of this pipeline stall, CPU sits idle, and we know that when the CPU utilization is not maximized, the performance is generally decreased. So because of this reason, pipeline hazards generally lead to the decrease in the performance of the system. So now let's talk about the causes of pipeline hazards. So talking about the causes of pipeline hazards, so these hazards can occur due to various dependencies among instructions, complicating execution and so on. So now let's go to the next slide. So now let's understand the pipeline execution. So the processor executes a program by fetching, that is FI, and executing, that is EI instructions. So as you can see in the first figure right there, so we have instructions, that is I1, I2, I3 belonging to a particular instruction stream. So each instruction will have two phases, that is F1 and E1 for I1, and so on, and similarly for I2 it is F2 and E2, and for I3 it is F3 and E3, and so on. So there are like basically two phases for each instruction in the instruction stream, and these instructions are all placed in a sequential way. So because of this reason, it is known as sequential execution. And now when you look at the second figure that is given, that is hardware organization of the pipeline. So basically we have two units, that is instruction fetch unit and execution unit. So in the instruction fetch unit, what happens here is the fetch unit will fetch the instruction for execution, and the execution unit will execute the instruction that is fetched. So in between these both units, there is a buffer. So interstage buffer B1 is used to store the fetched instruction from the fetch unit, and it is also used to pass the instruction to the execution unit for execution. So now let's go to the next slide. So now let's talk about types of pipeline hazards. So there are basically three types of pipeline hazards. So the first one is structural hazards, and the second one is data hazards, and the third one is control hazards. So now let's just talk about all these three in brief. So talking about structural hazards, so these arise from resource conflicts when the hardware cannot support all the possible combinations of instructions simultaneously in overlapped execution. So when the now when looking at data hazards, so these arise when an instruction depends on the results of a previous instruction that has not yet been completed or executed. Now talking about control hazards, so these result from branch instructions that alter the flow of instruction execution, complicating the pipeline's operation. So now this is all about brief introduction to all these three. Now let's talk about in deep one by one. So let's start with knowing structural hazards. That is, we'll explore what is structural hazards and so on. So talking about structural hazards, so if some combination of instructions cannot be accommodated because of some resource conflicts, the processor is said to have a structural hazard. So when a sequence of instructions encounters this hazard, the pipeline will stall one of the instructions until the required unit is available. So you can see in the figure that is given towards the left side of the screen. So we have so vertically, if you look at, we have instructions, that is I1, I2, I3, and goes on. And then when we look at the horizontal top, we have 1, 2, 3, 4, 5, 6, 7. That is numbers representing the clock cycles. So for each instruction, that is for instance, when you look at I1, there are four phases. So similarly for all the instructions, basically we have four phases, that is F, D, E, and W. CPU. So F represents fetch, D for decode, E for execute, and W for write. So in I1, it is the four phases are F1, D1, E1, and W1, all taking up just one clock cycle each to perform its operation. But when you look at I2, there is an operation called load that is taking place. So because of this load operation that is happening, there is an extra phase that is adding along with the four phases, that is F, D, E, and W. So the extra phase that is getting added is M2, that represents for memory. So because of this extra phase that is getting added, so when we look at the subsequent instructions, that is I3 and I4, there is empty phase that is getting created. So this empty space is called a pipeline stall. So because of this pipeline stall, what happens is the CPI value increases from its ideal value of 1. So when the CPU ideal, always the CPI's ideal value is 1. So when it's not equal to 1, basically what it means is the number of cycles per instruction is increased. So when the number of cycles per instruction is increased, the performance in fact decreases. So when we look in deep about this, so as the cycles per instruction is increasing, because of this the CPU sits idle for a particular period of time. So when the CPU sits idle, the performance is automatically decreased, as all of you guys know. So because of this, the pipeline, the performance is decreased because of the structural hazards. So when we look at some pipeline processors have shared a single memory pipeline for both instructions as well as data. So as a result, what happens is when an instruction contains a data memory reference, it will conflict with the instruction reference for a later instruction. So to resolve this hazard, we stall the pipeline for a period of say one clock cycle when the data memory access occurs. So stall is commonly called a pipeline bubble or just bubble. So this was all about. We have explored the structural hazards in deep. Now we'll talk about. We'll explore data hazards and control hazards in deep. So this portion will be taken up by Roshan Pranav. So thank you.
Yeah, so let's deeply dive into data hazards. And data hazards occur when an instruction depends on the result of a previous instruction that has not yet completed its execution within the pipeline. So these hazards can disrupt the smooth flow of data and lead to delays. So here's an example of how a data hazard works. Like here's a diagram parallel to the definitions. So you can consider a pipeline execution of these instructions like add R2, R3, R1, subtract R4, R1, R5 preceding the instruction. Here, the DADD instruction. Actually, a DADD instruction is a double word add. So it's a MIPS assembly language instruction used to add to double word integers. So here the DADD instruction writes a value of R1 in the WB pipe stage, and along with it the dsub instruction. So what is the dsub instruction? So it is also a double word, but a double word subtract. It is also an MIPS assembly language used to subtract one double word integer from another. So coming to this context, the dsub instruction reads the value during its ID stage. So this problem is called a data hazard as a delay is occurring in the situation. So moving on to the next slide, we can view the different types of data hazards. So starting with the first one, the RAW, read after write. This is the most common type of data hazard. So it happens when an instruction needs to read a data location that a previous instruction is writing to. So, in order to have a deep knowledge about it, let us consider a scenario where instruction A is writing to a register, and along with it, instruction B wants to read from the same register. So, at this situation, the instruction B must wait until instruction A completes its write operation. So, here comes a delay. So, moving on to the second type, the write after read. So this hazard occurs when an instruction tries to write to a location before a previous instruction reads from it. So although it is less common, it can cause issues, especially in out of order execution scenarios. So also have to have deep knowledge. Let us consider another scenario where instruction A reads from the register and instruction B writes to the same. So here the instruction B must wait until instruction A completes its read operation. So here comes an delay where instruction B has to wait for a long time. And we don't know how much time the instruction A would take for a read. So moving on to the third type, the write after write. So this occurs when two instructions write to the same location. So the challenge here is to ensure that the correct value is written last. So having a scenario, if instruction A and instruction B are both writing to the same register, the final value must reflect the correct sequence of operations. So here's the a brief note about the types of data hazards. So moving on to the next slide, we can see the control hazards. This is the third type. It is also known as the instruction hazards. So it is briefly classified as conditional branch and delayed branch. So before moving on to the types, we shall have knowledge about control hazards. So these hazards occur when the pipeline makes incorrect predictions about the flow of control, leading to the execution of incorrect instructions and hence causing delays. And control hazards arise from branch instructions that alter the flow control in a program. So when the pipeline encounters a branch instruction, it must predict the path of the program it will take. So if the prediction has gone wrong, the instructions that were fetched and partially executed must be discarded, leading to delays. So moving on to the conditional branch, a conditional branch instruction changes the flow of control based on a condition. For instance, an if statement that directs the program to different paths based on whether a condition is true or false. So the pipeline here must predict whether the condition will be true or false and fetch the corresponding instructions. So if the prediction is wrong, so it must discard the instructions and refetch the correct ones, which can be expensive. So we go on to the delayed branch. Delayed branch is a technique used to minimize the impact of control hazards. So in a delayed branch, the instructions following the branch are always executed regardless of branch outcome. So this technique effectively hides the branch delay by executing useful instructions while the branch decision is being made. Uh, the effectiveness of the delayed branch approach depends on how often it is possible to reorder the instructions. The main objective is to place useful instructions in these slots. So moving on to the next slide, we can see the techniques for hazard mitigation, like the effective strategies for managing these pipeline hazards, the computational architecture. So starting with the first one, the speculative execution. The executing instructions ahead of time based on predicted paths reduces the control hazard and enhances the efficiency. The second one is stalling. Introducing delay cycles helps manage and handle hazards effectively, ensuring smoother operation. So the data forwarding utilizes the output of a previous operation directly in the next operation, so it reduces the delays significantly. So these are the techniques which will be suitable for almost all the data hazards that has been discussed earlier. Moving on to the next slide, the impact of pipeline hazards on performance. So pipeline hazards mainly impact on CPU performance, as these pipeline hazards can lead to delays, and structural hazards can increase execution time up to 25%, because these hazards occur when multiple instructions require the same hardware resources, which again causes delays. So understanding and managing hazards is crucial for executing the CPU design, and regular monitoring and optimization strategies are vital for maintaining the performance, as continuous assessment and improvement of pipeline process helps sustain optimal performance levels. So that's it for the slide. This is a deep knowledge about pipeline hazards. Hope you enjoyed the presentation. Thank you.